we talked about being able to arrive at a position function given some initial conditions and a starting function for acceleration. So let's do an example where the acceleration function isn't a constant. So we're given that the acceleration function is e to the ti minus 8k. And our initial velocity is just some vector, and our initial position is actually the origin. So we want to figure out what the position function looks like. So let's bring some intuition to this in the first place. One is that I have negative 8k. So what that tells me is I'm going to continue accelerating in that negative z direction. So long term, I should really go low in the negative z direction. But I have something e to the t in the I direction, which tells me as t goes from 0 to positive infinity, that acceleration is going to continue to increase. So if the acceleration is increasing, the velocity should increase even more quickly, and the position value should increase ever more quickly. And notice that we don't have really any acceleration in the j direction, which means that if we have a constant velocity in the j direction, that the position will continue to move in the j direction, but we don't expect it to change because there's no acceleration. You just sort of coast. So those are some intuition pieces that we start with. Let's see if the mathematics that we get through here back up that intuition. So remember, if we're going to solve this, we want to arrive at a velocity function, but we only have an acceleration function, so we need to integrate or find an antiderivative for the acceleration function to find what the actual velocity function is. So if we integrate, or if we antiderive at least, this function, what we get is e to the ti minus 8tk plus some constant vector. And I'm going to call that c1. So really what I want to do here is I'm going to set that up as e to the t plus, maybe I'll just call that c, and I'll call this c1i plus c2j plus c3 minus 8tk, right? And so that tells me that that's actually the velocity function. That's the velocity function. But I want to figure out what these constants actually are. So I need to use that initial condition here. So if I plug in 0 for t, well, e to the 0 is 1. That doesn't change because that's constant. And 0 times 8 is 0. And I also know that my initial vector is that. So that tells me that I can solve for what C1, C2, and C3 are. So that tells me C1's got to be 1, C2's got to be 3, and C3 also has to be 1. What that gives me then is this vector function, or this velocity function, which is e to the t plus 1 I plus 3 j plus 1 minus 8t k, right? So I have a velocity function now, but I need a position function. So what we're going to do is we're going to integrate this velocity function, or antiderive it rather. So we want to antiderive velocity, and to do that, we're going to do e to the t plus 1 I plus 3j plus 1 minus 8t k dt. And so when we do that, we're going to get e to the t plus t I plus 3tj plus t minus 4t squared k. And we have some sort of constant, I'm going to call it d here. So if we use that d, if this has components d1, d2, d3, well, that tells me that my position function is e to the t plus d1 I plus 3t plus d2 j plus t minus 4t squared plus d3 k. So we can use the same methodology we did here. We filled it out, and we want to find, and we know that r0, we know it's going to eventually be the 0 vector, but let's plug it into this function. So e to the 0 is 1, that's just 0, so 1 plus d1 I, well that's 0, so d2j, and 0, 0, d3 k. All right, then we also know that the initial position is the origin, which tells me that d1 has to be negative 1, and d2 and d3 are actually both 0. So then if we're going to put that all together, we take this function and these constant values to write out our RT is, so here d1 is negative 1, so e to the t plus t minus 1I, and then we have 3t plus 0, so 3tj, and then we have t minus 4t squared plus 0. So we have this plus that minus that, t minus 4t squared k. So let's see if our intuition matches our values. Now, one thing we could do here, something we probably should do, is we say, okay, is that position function reasonable? Well, if I take r prime of t, I get e to the t plus 1 I plus 3j plus 1 minus 8t k. So it looks like I got the velocity function that I expected, so I feel pretty good about that. And then if I take r double prime, I get e to the t I plus, that's 0j, and that's negative 8, so actually it's minus 8k. So that matches my initial case, so I feel pretty good about that. So let's talk about the intuition here for a minute. This says that in the I direction, e to the t plus t minus 1 is our starting, this is our position. Now, when t is equal to 0, this whole thing zeroes out. But notice as t goes to infinity, t gets pretty large. Obviously, it goes to infinity, but e to the t goes really quickly. So what we're going to find is in the I direction, it's just going to zoom out. Which, again, makes sense. Our acceleration is rapidly increasing. So if our acceleration is increasing, it's increasing our velocity at a very fast rate. And so if our velocity is constantly going up, our position is going way out. Think of it like a car that keeps going faster and faster and faster. You're eventually going to travel very, very far, very quickly. Now, in this particular case, 3tj is our position. That just tells me that we're just poking along at 3t. Whatever the time is, or 3 times that, that's how far we've gone down the road. And that makes sense because we don't have any acceleration. Velocity isn't changing, but we do have a constant velocity we started with. So it just kind of goes and just kind of pokes along. And then in the k direction, when t is 0, it doesn't really go anywhere. And we actually started in the positive direction, but since our acceleration is negative, we start going up, but then we really quickly pitch down, which is how this behaves. Because in the range of 0 to 1/2, this value will actually be positive. But as soon as time hits 1, it's actually not even 1/2. It's some other number. I'd have to think about it. I guess it's t equals 4. Wait, no, that can't be right. T equal, see, anyway, I'm off. But t equals 1/4. That's, gosh. All right, so when t equals from 0 to 1/4, it's positive, and then after t goes past that, it starts going negative, and continues to go very quickly as t goes to infinity. So the reason we want to do all this is always good to develop good intuition about what you're trying to look at. Say, does my answer actually make sense for the inputs that I'm given? And what we see is that that's correct. It does obey the initial conditions. And that's how we get these kind of functions through integration.